time, but I teach
every year, the 40 faculty of the Integrative Center for Learning and Memory nominate and then vote on that year's distinguished lecturer for the center. And it's my pleasure to tell you that this year we have Kate High as the person that the faculty chose by a great margin, actually. There were lots of nominations, but everyone picked you, Kate, so it's really a pleasure that you're here. Kate did her Ph.D. with Patricia Yanek at UCSF, and it was clear from early on she was going to be a star, actually. It's really quite impressive how for certain people, you know, there's distinguished, beautiful work from the first time they enter science, and this was clearly the case with Kate. She studied cue-reward learning and extinction in Patricia's lab. She published this really great Nature paper, where for the first time, she showed that in cue-reward learning, synaptic changes in the amygdala, synaptic strengthening in the amygdala, and specifically in thalamic lateral amygdala synapses, not cortical, which is interesting, that these changes were critical for cue-reward learning that she studied that. After that and other contributions in Patricia's lab, she went on to Stanford, where she did a postdoc with Carl Weiser. And once again, there too, she published this really impressive paper. I remember reading it, actually. At UCLA, we have a depression grand challenge. And Kay showed that these dopaminergic neurons were critical. The midbrain dopaminergic neurons were critical for depression-like behaviors. And she could modulate them up and down with this powerful technology that Carl developed. She could manipulate depression by manipulating this group of neurons. It's really a very interesting, very striking paper. Then she moved on to the Picower Institute at MIT, where she has a lab now. And once again, a never-ending stream of high-profile papers that have awed her large Twitter following and the rest of us. She continues to study positive and negative valence memories. She also studies a number of other topics, including social behaviors. And I remember visiting her at MIT a couple years ago and just being floored by a study that she eventually published in Cell on loneliness. So I just thought that, you know, our society is plagued by loneliness, and Kay actually studied it. And she was able to manipulate loneliness optogenetically and get to the biology of it, which, you know, it was just one of those beautiful studies that, you know, stay with you. And I remember, you know, for days afterwards thinking about that work. And then when it came out in Cell and I read it in detail, I was really, really impressed. But I'm not alone. Hey, he's a real star. No pun intended. She, understandably and not surprisingly, has gotten a bunch of awards from the early days of her career. It started with the Donald Lindsley Prize for the most outstanding PhD thesis that she got while still a graduate student. And this year alone, she got 3 major awards, actually. The Presidential Early Career Award, which, you know, if you're a really hotshot young scientist, that's what you get. And that's what she got. The Daniel Freeman Award and the Society for Neuroscience, the Young Investigator Award. You know, some people get all these awards, and some of us have mixed feelings about it, but she truly deserves it. She truly deserves it. I mean, she's really wonderful. And without further ado, Kay, please.
Thank you for that lovely and embarrassing introduction. No, it's my honor to be here today at UCLA. I've already had some really fun conversations, and I'm looking forward to lunch and more conversations in the afternoon. So I just decided to go a little bit rogue for today, so I just changed the talk I was going to give to be able to tell you guys about 2 unpublished stories in the lab, just because that's more often than me. I'll start with a little movie, and I apologize if, how many people here have seen the show Westworld? Yes. Okay, well, if you haven't gotten to see to episode 8, then I apologize. It's a spoiler, but if you haven't gotten there at this point, then you're not that into the show, so I don't want you to do that. But basically, Anthony Hopkins explained something that I really liked, and in this scene, so if you haven't followed the show, it's about basically these lifelike robots and how to essentially engineer consciousness. So in this particular scene, which is, this is a spoiler alert, Bernard is someone who was an engineer of these robots and that is now discovering that he himself is actually one of them. And Anthony Hopkins asks him to reflect. So
I wonder, what do you really feel? After all, in this moment, you are in a unique position. A programmer who knows intimately how the machine works, and a machine who knows its own true nature.
I understand what I'm made of, how I'm coded, but I do not understand the things that I feel. Are they real? The things I experienced.
okay, so I apologize that this movie didn't actually play. Hopefully my other movies play, but I think that one thing that Anthony Hopkins touches upon is that emotion is something that is very well conserved function in our brains, but something that we understand very little about. And so it might be one of the greatest remaining mysteries of the human brain. So, slides. Having a technical problem here. Okay, so very, very simply put, I'm interested in how we know if something is good or bad. How do we assign positive or negative valence to environmental stimuli? What I'll talk about today is primarily auditory Pavlovian conditioning. So if you hear an auditory stimulus, for example, a gunshot, you might form a negative valence association if you've had previous experiences where this predicted threats. But it's also positive that any previously neutral auditory stimulus, like a gunshot, could be paired with some positive experiences. For example, Usain Bolt, maybe if he hears the gunshot, he just thinks about all the little medals. Or if you hear these sounds all the time, then perhaps they signify no motivational consequence, no motivationally significant consequence. And so therefore, they're boring. And so this is just a very, very, very simplified view of the two-dimensional theory of emotion, where we have arousal or intensity on the y-axis and hedonic value or valence on the x-axis. And I'm very interested in the neural circuitry that underlie the process where, you know, we're constantly navigating this environment and bombarded with a barrage of sensory information. And from that, we need to filter out what is important and what is unimportant. And so, presented, we need to first determine if this stimulus is important, something along the lines of an absolute value. If it is not important, we ignore it. If it is important, we must then determine if it is positive or negative. If negative, we avoid. If it's positive, we approach. And again, very, very simple, but I think it's an important starting point for determining these processes. So I'm going to talk about this process today. So as I mentioned before, amygdala circuitry is relatively well conserved. Even reptilian species that have hardly changed for millions of years have amygdala circuits. And so if you're interested in this from a sort of basic science perspective, it's great to understand how simple circuits work to help us understand more complex circuits that we see in cortex. But if you're interested in translation, it's also important to think about what we're studying in a mouse might actually be relevant for understanding psychiatric disease in humans. Okay, so very, very, very simply, I'm going to summarize a lot of our published work in a slide or two. Today, I'm just going to talk about the basolateral amygdala, so the VLA, the basolateral amygdala, the basolateral complex. It's actually thought to be sort of a primitive cortical-like structure, and that it is mostly glutamatergic neurons, and associations are formed within. Today I'm going to talk a little bit about outputs, projections of the basolateral amygdala that go to either striatal structures, the central amygdala, which is predominantly composed of medium spiny neurons, just like the nucleus accumbens, and the accumbens, I mean, of course the structures are different, but the accumbens is ventral striatum. And so how do these neurons that project to different striatal-like structures compare to each other, and how do projections to cortical regions, like the prelimbic subregion of prefrontal cortex, how do these different populations of neurons in the BLA function? Okay, so what we do know, and this is summarizing some of my work as well as work with many other people, including Ainslow and Joe Ledoux, and many other field leaders. A tone can be presented, an auditory stimulus, and if that tone is paired with, for example, foot shock, there is a good amount of evidence to suggest that Hebbian plasticity mechanisms occur to allow selective or preferential strengthening of inputs carrying putative tone information onto these basolateral amygdala neurons to be potentiated. And we've shown this with a number of experiments, but one data slide I'll show you here is showing using AMPA to MD ratio, which is a proxy for glutamatergic synaptic strength. When we stimulate putative auditory thalamic inputs coming in following fear conditioning, if we label neurons that are going from the basolateral amygdala to the central medial nucleus, we can see that in these neurons, we see a potentiation of synapses following fear conditioning and a depression of synapses, or at least a reduction in amplitude ratio following reward conditioning in these BLA to CEM neurons. However, if we expose an animal to a tone that is paired with sucrose, we actually see a relative strengthening onto these accumbens projectors. So if we instead trace, using a retrograde traveling fluorescent sphere, retrobeads, injected into the nucleus accumbens and trace basolateral amygdala neurons, we see that amplitude ratio following fear conditioning actually is reduced, and that there's an increase in amplitude ratio following reward conditioning. So opposite synaptic changes were happening depending on the projection target of these neurons. And one key thing that I'll come back to later in the talk is that in reward conditioning paradigms, we must food restrict these animals, and that's what the FR stands for here. We food restrict animals to get them to learn the task. And what we happened to notice was that actually the naive groups are different in BLA to accumbens projectors when we compare just naive animals that just either undergone food restriction or not. And so this was sort of something that we didn't, this wasn't what we initially set out to study, but an observation that we took note of and wanted to follow up on. And so that's one of the projects that I'll tell you about today. Okay, so to summarize some of our other experiments, if we photostimulate basolateral amygdala neurons projecting to central amygdala, we see place avoidance. And if we, this central medial nucleus of central amygdala, and if we stimulate BLA neurons going to the nucleus accumbens, we see approach or support of intracranial cell stimulation, consistent with what Garrett Stuber and Tonegawa have shown. But today what I want to talk about are these two kind of current questions that I'm really interested in thinking about. Number one, how does homeostatic need alter emotional circuitry? Specifically, for example, hunger. And how are competing motivational drives orchestrated? We do a lot of work using these reductionist behavioral paradigms where animals are trained to associate one thing with one other, with a tone with a foot shock, for example, or a tone with sucrose. But what happens when these animals are navigating the wild and forced to sort of orchestrate these competing mechanisms? Okay, so the first question, how does homeostatic need alter emotional circuitry? And this work is being carried out by Gwendolyn Calhoun and Amy Sutton. And this particular project is, I hope, halfway done, but quite a lot to still do. So this is sort of midstream and a good place for us to get feedback. So I'd love to hear any ideas if you guys have them. So one thing that we observed from a previous study, which I don't have to talk about today, but where we recorded from many, many neurons that were photo-identified in the basolateral amygdala. And what we wanted to look at was what these neurons do during retrieval, during Pavlovian discrimination. But what we happened to also observe, sort of serendipitously, was that if we photostimulate these neurons that are basolateral amygdala to central medial projecting, we see a lot of neurons that are photoinhibited. Same can be true for Cummins projectors, and that even though the neurons that we identified as expressing CHR2 using our phototagging approach, which is essentially just recording the optrode and then using light to identify which neurons were actually expressing channel rhodopsin and therefore had the anatomical or genetic features that we're looking for. In this particular case, we're looking for neurons that had a defined projection target, either just central medial nucleus or the nucleus accumbens. And although we found about the same proportion of neurons that were photoidentified, the number of neighboring BLA neurons that were inhibited was significantly greater for BLA to central amygdala photostimulation. And so this sort of raised a question that we have been thinking about for a long time. You know, why are there these functionally distinct yet intermingled populations of neurons within the basolateral amygdala? What's going on? How do these neurons interact? What might be the possible connectivity? One idea, actually inspired from work from Andreas Lucchi's lab, thinking about how these neurons might interact, is just perhaps they do so because the interneurons between them allow for greater interaction. So the first thing that we initially thought was maybe there would be mutual inhibition between neurons that encode reward or aversive or negative valence principal neurons, these projection neurons. That was one idea. Another possibility, which at the time I just listed because it's theoretically a possibility, I didn't actually think it would be a likely outcome, would be that there could be a unidirectional inhibition, an asymmetric effect relationship between these populations of neurons, or the possibility that there's a mutually excitatory relationship, which is also possible given that the amygdala is an epileptogenic region, and so there is known to be some recurrent excitation. So what we did, or what Gwendolyn Calhoun set out to do, was to explore the nature of the relationship between these populations of neurons. And so I don't have time to tell you about all of the experiments that we did, but if we selectively express channel rhodopsin in BLA neurons predicting the central amygdala nucleus by injecting a retrogradient traveling viral vector expressing pre-recombinase into the downstream target, and then a pre-dependent viral vector allowing for the expression of channel rhodopsin, we can selectively express channel rhodopsin in this population of neurons, and then label another population of neurons, these nucleus accumbens projectors, with a fluorescent retrobeam. And then stimulate this population of neurons and ask about what types of connections between this population and this population of neurons exist. And we did the reverse experiment here as well. And I'll just say, long story short, we did a number of different experiments, but in every case, we saw that there was both an inhibitory postsynaptic current and an excitatory postsynaptic current, and in all cases that the latency for the EPSC onset was shorter than that of the IPSC onset, and if we use the Crackham approach, applying TTX and 4IP to block network activity and amplify the signal, an approach developed by from Carl Swoboda's lab. We can determine that there are monosynaptic connections that are excitatory and polysynaptic connections that are inhibitory. But, okay, so there's, both types of inputs, but at the end of the day, I would think that spiking would be required to drive behavior, so we're interested in the net effect. What is the output? So we next did a similar set of experiments, here stimulating in each population and then recording in the other. And so this is a little bit of a dense slide, so I just want to orient you that the columns here are the neurons that we're patching and recording from, and the columns are the population of neurons that we're optogenetically photostimulating. And here, this is the naive condition. These are animals that were just plucked out of the cage with no manipulation. So what we found is if we photostimulate these central amygdala projecting BLA neurons, and we use interleaf sweeps where we inject a minimal current step and then alternate the sweeps where we photostimulate or not. and ask what the impact of this photostimulation is onto the other population of neurons. We can see that photostimulating central amygdala projectors tends to suppress firing rate in these nucleus accumbens projectors. Of course, it's possible there's just lots of local inhibition, and so we wanted to do the important control experiment of recording and stimulating within the same population. So here we're just patching onto neurons that were just so happen to be retrograde positive, but not CHR2 positive. And what we see is that when we record and stimulate from CEM projectors, that we see an increase facilitation of spiking. And also, if we do the same thing with the Cummins projectors, we see sort of, a wash, not really a strong effect in either direction. So nothing significant. And then the big surprise to me was that if we photostimulate the Cummins projectors, which are predominantly reward encoding, and record from these central amygdala projectors that are predominantly aversive encoding, what we see is actually a facilitation. So this was very confusing to me. Did not understand this. I do want to point out that if we start this 10 hertz train, it looks like a bar on the slide for some reason, but this is just 10 hertz pulses. When we start this train before the current step, it does not on its own cause spiking. So it's not sufficient to cause spiking on its own, it just facilitates spiking when the cell's already depolarized. But still, this was very confusing. How can it be possible that what are generally, functionally opposing populations of neurons would have this asymmetric relationship? So, just to summarize what I told you in a little schematic here, again, these central amygdala projectors inhibit nucleus accumbens projectors, and nucleus accumbens projectors seem to facilitate spiking in these central amygdala projectors. And again, these are all basolateral amygdala neurons that are just projected to different targets. But how does this make sense? Why isn't it this pretty picture of symmetry that I kind of expected to see? When I think back to the synaptic changes that occur following fear and reward conditioning in these accumbens projectors and central amygdala projectors, there's this, beautiful double dissociation. So why are we getting this asymmetry? This makes no sense. But then, of course, I have to remind you that in the reward conditioning, it's not really fair to say that this is an oversimplification, right? Because in this condition, the animals are food restricted. They're in a different state than the animals that we use for fear conditioning, which are not food restricted. So I'm going to now point you to a couple of, shadows or clues in the data. And so when we published the paper, we're sort of like, things didn't work out all perfectly, and we're sort of trying to figure it out. And at the time, we sort of brushed some of these things off as, it's biology. But actually, some of the inconsistencies or inherent inconsistencies are actually clues that something really interesting is going on. And so this is my favorite thing, to sort of follow up on things that don't quite make sense, and usually there's something really interesting lying beneath. And so what we did in our previous paper, in Pranit's paper, published in 2015, he found that if we photoinhibit, this is expressing halo rhodopsin bilaterally in projector populations in the PLA, if we fear condition animals and we photoinhibit these CEM projectors, we see an impairment in fear conditioning, a reduction in freezing, which was sort of consistent with our mental model. And this is, just one little panel out of many. If you're interested, please check out the paper. But then the thing that was strange, I would have expected to see all these lines on top of each other, and then the green line should have, in my mind, based on my working model, should have been right here, that inhibiting accumbens projectors, if they're important for driving reward, should have impaired reward conditioning, or reward conditioning and this Pavlovian conditioned approach. And that was confusing to me that we did not see that. In fact, not only did we not see a reduction in impairment with accumbens projectors, we actually saw an enhancement when we were inhibiting these CEM projectors, which, that was strange to have a loss of function manipulation and then an enhancement in a behavior. That was unusual. And so that was sort of surprising, but perhaps this speaks to the ability of these central amygdala projectors to be, to have a different level of control over neighboring neurons. And so one of my favorite things that I usually like to talk about is how, when we do these optogenetic manipulations, we're looking at what's happening overall, but this is not really, optogenetic tools tell us what neurons can do. They don't tell us what neurons naturally do. This occludes our ability to see any heterogeneity within the populations. And what we're actually looking at is really a majority vote. And I've used that sort of metaphor. Obviously, not everybody in our country agrees on who should be president, but we have a single president. And I used to think about this in terms of the majority vote, but now I'm sort of revising it and thinking, not all neurons are equally influential, and maybe it's more like an electoral vote. So anyway, another little clue here was when we photostimulated these neurons in naive animals and we observed a place avoidance with CEM predictors, we were not able to reproduce what some other groups, like John Britt, has showed from Antonello Bacci's lab, that stimulating BLA to nucleus accumbens terminals produces place preference, and when we stimulate the cell bodies, we don't see that. And again, one other caveat that I really want to say is that stimulating the terminals of neurons is not the same thing as stimulating somata of neurons that project to that same terminal. We have many examples of how we get different behavioral outputs when we stimulate terminals and stimulate somata, even if it's of that same projection. But okay, so there are some clues that perhaps we should have predicted this, and perhaps I should have known that it was going to be an asymmetric effect. But why might the brain even work this way? Why would it be logically advantaged? Like, why would this, be the way that the system functions? What would be the evolutionary reason? And so one idea was, okay, if in the wild, animals are engaging in reward-seeking behavior, whether it's social behavior or feeding or going to the water hole, seeking rewards almost invariably exposes animals to increased risk for predatory threats. And so, perhaps, this is wild speculation at this point. I do want to say this is wild speculation, but this is just how I'm thinking about it. Feedback's welcome. That reward-seeking might just be inherently risky, and that if that's the case, perhaps priming circuits that are important for escape might be a good insurance policy. And so this is one idea. And if you think about examples from the wild, this is absolutely true. If you look at animals under different homeostatic need states, for example, a lioness would rarely attack even a juvenile elephant in broad daylight without a pack, right? This is something that lioness would rarely do alone. But in near starvation situations, lions will engage in behaviors that they normally wouldn't. Similarly, baboons would rarely forage in water because of the risk of being attacked by caiman, which is a major threat. But in scarce resource availability conditions, foraging in water suddenly becomes something that they'll do. So you'll see this in certain need states. And so we wondered if 24 hours of food deprivation, which is not very much, and something that at least previously we did all the time without even really thinking about it. We just kind of food stripped animals all the time. And I didn't really consider how this might have widespread impact on the rest of the brain. So we asked the question, how would the local interactions between these populations of neurons qualitatively change under food-restricted conditions? So the first, the most striking change is that if we previously I showed you that photostimulation of central amygdala projectors and reporting from accumbens projectors produced a suppression of firing. Now, following 24 hours of food deprivation, we see a robust facilitation. And if we photostimulate and record from accumbens projectors, we now see a facilitation where previously we saw essentially no effect. We still see a facilitation for CEM projectors, and we still see a facilitation from activating accumbens projectors to CEM projectors. And so, this is still a work in progress, but at least thus far seems to be pretty robust. And so what I've just told you in this work in progress is that there exist robust and pervasive local interactions between these populations of neurons. We're also exploring their relationship with other projector populations, BLA projectors from the campus, for example, and that the relationship between these competing circuits is state-dependent. And so in the lab, we sort of fondly refer to this project as like the hangry phenomenon, which I'm guilty of having. So So here is just a movie, and this is what we hope to pursue. Is here I'm just showing you a very preliminary movie of BLA neurons that project nucleus accumbens, so we're selectively expressing GCAMP in BLA to accumbens projectors, presenting a grin lens, and then imaging over the amygdala when animals are performing pavlovian discrimination. We want to see how these neurons change across different need states. And though I'm typically an electrophysiologist by training, I appreciate the advantages of imaging. Particularly, we want to be able to follow the same neurons across all these different kinesthetic need states. And yeah, I know, Josh is probably like, you should have gone to neuro lab or school, but now I'm keeping myself too. But yeah. So that's essentially how far we've gotten with this story, and that's something that I'm really interested in, and how a lot of manipulations that we do can change the sort of basal state of the brain. Another project that I'm very interested in is, so that's just looking at this interaction here. Another project that I'm interested in are how are competing motivational drives orchestrated. I just mentioned that, in the wild, animals have these competing forces, but by the time you're kind of outputting to striatal structures, I feel like actions are, in the process of already having been selected. So how does the brain, navigate this other function? Okay, so the next project I'm going to tell you about is exactly this, and this project is being led by two postdocs in my lab, and very late at night I decided to include this. This is really silly. Okay. So I have two young children, and this kind of shows you what I mostly watch. I don't usually get to watch my squirrel. But see here, Gus is engaging in this food scene behavior, very naturalistic, as you can see. And then when met with a predatory threat, he doesn't try to hold on to his food, right? He engages then fully and commits to escape behavior. And so, sorry, that was really silly, but so this is a project that Anthony Burgos-Robles and Al Kimchi in the lab have been working on for quite a few years, and I'm pleased to say it should be out soon. So the questions that we had were, how are representations of emotion, how is emotion represented, and are these representations stable within the amygdala when there is an actual conflict, there are competing motivational drives, and where is this represented? Where might the directionality flow of information be? In this task, we sort of devised a new task. Denis Perret has also done some beautiful work on this, but very different and more naturalistic foraging task. Here, what we're doing is we're training animals to do Pavlovian discrimination. So one conditioned stimulus predicts sucrose. At the end of the sucrose tone, there's a vacuum that sucks away available sucrose. And this next part of the study is in rats, actually. And then another conditioned stimulus predicts shock. And then in competition trials, there are pseudo-randomly presented either these conditioned stimuli on their own or what I'm going to call competition trials, which are both of these conditioned stimuli and both of the unconditioned stimuli as well. And we want to ask how the animals perform when we present these competition trials. And so if we look just on a population level, how animals perform when each of these trials are presented. If we look first at reward-related behavior, just meaning port entry, when we present the CS sucrose, the sucrose cue, we see mostly port entry. When we present the shock cue, no port entry. And we present the competition cue, you see something in the middle, and this little burst of port entry at the end is actually a response to the vacuum. Sometimes animals hear the sound of the vacuum and then it sort of run over. Then we also look at fear-related behavior, freezing, and when we present the CS shock, we see increased freezing, not much freezing with the sucrose CS, and then sort of the mixture with these competition trials. But again, I'll just say this is when we're looking at the population, all the behavior from all the animals is population. So I'll come back to that as well. And so what we were doing here this is Tony's work. He was simultaneously recording in prelimbic and basolateral amygdala during this particular task. And what we found was there was very heterogeneous responses. That's not particularly surprising. So here what I'm showing you, this is our shorthand. This is neurons that were excited to the reward predictive cue, and here is the reference event, which is the response of neurons in the prelimbic cortex in response to the sucro-CS. Here is the response to the shock predictive CS, and hot colors are excitations, blue inhibitions, and then here are the neurons that were selectively excited to the shock predictive cue. That's F plus, just our shorthand. And you can see that there is substantial diversity of different responses, and we're only showing you neurons that had some sort of task element response here. If we look at the basolateral amygdala, also heterogeneous responses. I will point out that indeed we found that there was sort of somewhat of an overrepresentation, if you will, of neurons that were excited to the shock predictive cue in the prelimbic cortex, and that these neurons had more correlated activity with BLA than other neurons. Okay, so in the basolateral amygdala, we also saw heterogeneous responses, and here I'm just showing you a representative periovascular histogram. Typically in the BLA, this is what we see. We see a phasic excitation, and then basically goes back down to baseline. And we do see sort of heterogeneous responses, neurons that respond similarly to both conditioned stimuli, for example. Okay, so there's all sorts of different responses. That's not surprising. But how does this break down? And so if we look at PL populations, and I'm just going to show you one way that we sort of data population. So we take individual neural responses, and then we ask, okay, did this neuron have a significant response to the reward predictive cue, the sucro-CS? If so, was it an excitatory response or an inhibitory response? If it was an excitatory response, the next layer of jello is we ask if this neuron responded to the shock predictive cue or not. If so, was it excitatory or inhibitory? And then, okay, here, for example, we follow this tree, this branch down the tree. We see that there are some portion of neurons that showed excitations to both the sucrose and shock predictive CS. If we look at the whole tree, you can see that there's a diversity of responses, actually quite a significant, a substantial proportion of neurons that are excited to the shock predictive cue in PL. And if we look at this in terms of the bias, looking at Z-score to the sucro-CS versus shock CS, we can see that there is a bias in the prelimbic subregion of PFC. If we look at BLA using a similar approach, we don't actually see much of a bias. So BLA neurons, if we don't identify any features of them, and you just record them non-specifically, we see almost a 50-50 split in terms of the bias responses. So the next thing we wanted to do was look at what the interactions are. So we know that BLA and prelimbic cortex have reciprocal connections. They're interacting with each other and also share a lot of common inputs and outputs. And so what's actually going on in terms of information transfer between these two regions? And so the first place to start was to look at cross-correlated activity, either excitatory interactions. This just means that these are all referenced to BLA spikes, because I live in a BLA-centric world. And, so that we're looking at PL spikes relative to BLA. So basically we ask, what is the latency for PL spikes relative to each BLA spike? And if they spike together, we see an excitatory correlation. If they are anti-correlated, if BLA spikes sort of, predict silences in PL, then we would see an inhibitory correlation. So this is just a cross-parallelogram, how to read a cross-parallelogram. And then we ask the question of, how does the nature of these interactions change when we're looking at these interactions across different epochs? And so Tony Burgos-Robles, who trained in Gregory Perk's lab, and Gregory Perk's done some lovely work looking at these interactions. But what we wanted to do was compare the interactions and the directionality of such an intertrial interval during the actual presentation of the sucrose cue and the presentation of the shock CS. And so we wanted to ask, to what degree when we look at these excitatory correlations, how often is the PL spike leading? Is the PL neuron spiking first, or is the BLA neuron spiking first? And we wanted to look at this. And so what we found is that across these different epochs, the intertrial interval, which basically baseline, or during the sucrose cue or the shock cue, we actually see that during the presentation of this shock predictive CS, we see an increase in the directionality of BLA leading the excitatory correlations. And so that was interesting. And then we also looked at what happens with inhibitory correlations, and I will say an important caveat is that we saw far fewer inhibitory correlations, but there did seem to be a trend towards BLA leading in the sucrose predictive cues. But I wouldn't put too much weight on that one since we have a small sample size. But in terms of thinking about the directionality of information flow, it seems like maybe, since BLA is leading in these cross correlations, maybe information is actually going from BLA to PL, but who knows, right? I mean, there's a lot of shared inputs, and the timing in these cross correlations it's not. We're using bins that are sort of large and not allowing us to see with a lot of resolution. If it's really monosynaptic, how much of this is directly information translated or transferred from BLA neurons directly monosynaptically to PL. And so we wanted to see if this was a direct connection. And so we use this approach, this photo identification, phototagging approach, whatever you want to call it. And I do want to emphasize that the very important caveat whenever doing phototagging is the problem of recurrent excitation. It's a big problem in any region where there's known recurrent excitation, hippocampus, cortex, amygdala. And so one big issue is, how do we know when we put our optro down here, we shine light, great, these neurons spike, yeah. But if a neuron spikes that we recorded from, how do we know it's not just receiving excitation, is actually just connected to a CHR2 expressing neuron, but not actually a CHR2 expressing neuron? That's a pretty big deal. And so in our previous work, we showed that different populations of BLA neurons, this is Anna Baylor's work, I actually didn't have time to talk about it today, but Anna showed that within the BLA, different populations of neurons actually had different thresholds for photoresponse latencies. And so, when you put the optical fiber in, it's impossible to know exactly how much light is going to be seen by each neuron because, light propagates sort of non-linearly through brain tissue. And so how much light is that seeing, and that impacts the response latency of the actual neuron that is expressing channel rhodopsin. So we wanted to characterize the photoresponse latencies in these responding neighbors when we can record ex vivo and unequivocally determine which neurons are expressing channel rhodopsin or not. Okay, long story short, and we did this important control in this study as well and identified the photoresponse latencies appropriately. And so if you're interested, I'm happy to talk to you about that in more detail. But actually what we found was pretty interesting. So if we identify these BLA neurons that project to the prelimbic cortex, here I'm just showing you a paragraph histogram where we shine pulses of light. We actually use many different light pulse or parameters to see what's going on, but essentially you can see that these neurons are responsive to light, and what we see in this subpopulation of neurons is that a lot of these neurons are responding to the responding in an excitatory fashion to the shock predictive cue, but sort of disappointingly, it's still pretty heterogeneous. I mean, even these photo-identified neurons are not all doing the same thing by any means. And we also observed that there were BLA neurons that were inhibited by these BLA to PL cells. And so we see some, which we'll just refer to as network-inhibited neurons, that were inhibited when we shine pulses of light into the BLA when we're expressing channel rhodopsin in these BLA to PL neurons. And that's just a little reminder of what we're doing here. So, okay, so this is sort of, scratching our head. This is not a simple answer, perhaps. But we wondered if the representation of, what do I mean by pure emotions? I just mean the state that is evoked by presenting either of the stimuli that predicts shock or sucrose is presented on its own in these sort of discrimination cases. is that representation stable when the animal is presented with a direct conflict, this co-presentation of these stimuli that sort of elicit competing motivational drives? And so we wondered if we could decode the activity of the, to predict the behavior of the animal by decoding activity during these competition trials based on discrimination trials. Okay, so that was a little bit confusing, so I'll try to make that more clear. So again, I'll remind you in our competition sessions, we have a pseudo-random schedule where we present condition stimuli that predict shock, condition stimuli that predict sucrose, and then sometimes these competition trials. And so now, previously I showed you just the population activity, the average behavior of all the animals. Now I'm showing you a representative rat, and this is a behavioral raster. I know it sort of looks like a neural raster, but this is the behavior of the animal, and red means freezing. So I'm just showing you each trial. Each trial that we presented, the CS shock across the session, what the animal did. You can see the animal does a lot of freezing when the CS shock is presented. Blue means port entry, means being break in the port. And this particular animal, on a trial-by-trial basis, pretty reliably goes to the port whenever the CS sucrose is presented. And then when we present the competition trials, this wasn't really observable if we just look at the population data animals overall. You just see like something in the middle. But that's not really what we see. If you look at trial by trial, it's kind of remarkable. A lot of many of the rats that we included in our experiment showed something where the animal basically selected one of the two behaviors, either port entry or freezing, for the duration essentially of the trial, which is, the cue's on for 20 seconds. 20 seconds is kind of long, so it's definitely possible. I would imagine, maybe the animal freezes a little bit and then it gets a little bit super, then freezes a little bit more. They can totally waffle. There's time to waffle, but that's not what happens. The animal commits essentially to one or the other in these conflicting situations. And interestingly, we also look, okay, what determines what the animal does, right? There's sort of an exception here where the animal did waffle, but the majority of trials, the animal's sort of sticking to the plan. And what determines what the animal chooses to do? And we looked to see if the previous trial type, there's like a prior that predicts what the animal does, we cannot see any relationship between the prior trial type and what the animal does here. So we were very interested in this. And this was something that, we didn't predict. This is just what we observed. And this is, to my knowledge, the first time anyone's done this task. So we had no way of knowing exactly what we're going to get. But now this allows us the ability to ask, well, since the animals do different things on each trial, we can determine if we use the data from these discrimination trials as training data, and then plug that into a support for vector machine, just a simple supervised machine learning, classifier, where we looked at each individual neuron and do some dimensionality reduction on the neural data, and then look at what predicts the behavior. So port entry responses are on this side of the plane, so you can see, when the CS sucrose is on, the animal does port entry. If the CS shock is on, the animal freezes. That's not particularly surprising, but what we want to know then is, can we use these training data from completely different trial type to predict the behavior of the animals when both of these stimuli are presented simultaneously? This was something we were interested in because the environmental stimuli that we're presenting are identical, right? Every single one of these trials, it's the same, stimulus. It's the combination of the CS sucrose and CS shock. It's the same every time. So why are the animals not doing the same thing every time? And how do these neurons contribute, these PLA, the PL neurons, how do they contribute to determining the behavior? And again, I should say that is, still much to be done on this. So then what we did is, asked again each individual neuron, how did the animal perform? All of these are competition trials, and we just look at what predictions were correct or incorrect for predicting freezing or predicting port entry. But this, sort of unexpected trial structure allowed us to ask this question. So what we observed was, again, this is just a little chart to remind you of the neurons that we're recording. We plop our electrons down to BLA, record from a hodgepodge of unidentified BLA neurons, as well as BLA and PL neurons, as well as these network-inhibited neurons. And what we observe is if we look at BLA neurons overall, we see that, we see that, these neurons do an okay job, significantly above chance, but not particularly impressive job of predicting the behavior of the animals, similar to PL neurons, that were not much better than BLA. If we look at network-inhibited neurons, these neurons perform slightly better. And if we look at BLA to PL neurons, these neurons perform even better. And so a lot of times when you think about decoding neural representation, people think about the, you can't really, the thing that people often say, my primate physiology friends will say, you can't decode the behavior of an animal from a single neuron. You really need the whole network. My question would be, well, would you need the whole, is it a reason that you need the whole network because you don't know which neurons to look at? And certain information is being carried by certain populations of neurons, perhaps more than others. So, okay, so this is great. We did some sort of basic machine learning statistics to sort of test whether BLA to PL neurons can predict behavior, and it seems like they sort of can. But what's actually going on? So this set us up to sort of test these hypotheses, and we've now wondered if photostimulating BLA neurons going to PL could promote one behavior or another. And so first we did this in just discrimination, stimulating pseudorandom trials. And indeed what we found was that during shock trials, we saw an increase in freezing behavior. But this behavior was relatively subtle change. Like if we stimulate these neurons regularly, we don't see innate, like if we just stimulate a naive animal, BLA to PL, we do not see freezing. That does not on its own produce freezing. It's only enhancement of freezing during the CS shock presentation. And of course, it's really important to control for all sorts of caveats like axons of passage and backpropagation. And we're putting our fiber over PL, but how do we know we're not targeting all sorts of other regions within the medial prefrontal cortex? And so what we can do is, again, express channel rhapsody here, and then implant a cannula as well as an optical fiber that allows us to infuse either vehicle or glutamate receptor antagonist cocktail in a counterbalanced manner into the prelimbic cortex to determine if vesicle release at the level, transmission, synaptic transmission at the level of BLA to PL is actually required for this effect. And if we do this during this competition session, we again observe the same effect. It's blocked by these glutamate receptor antagonists. And we also see the same effect during competition, a bias that's stimulating when we just have the vehicle, stimulating BLA to PL, indeed drives freezing in these competition trials. We also wanted to see if this projection was necessary or for driving this behavior. We bilaterally inhibited projections from BLA to PL and again, did a similar manipulation where we inhibited BLA input to PL in a pseudo-random manner in this competition trials, and we observed the opposite to be true, that inhibiting BLA to PL input reduced freezing during the shock cues, and slightly reduced this, although this is sort of a wonky data set, during the competition trials. And we also showed the same thing using a chemogenetic approach that is in a block design. So, okay, just to summarize what I've told you today, that behavior, in this sort of particular conflict situation, a choice is made and maintained, and that seems actually relatively adaptive. Waffling is actually probably not very adaptive. It probably makes sense to select an action and execute it. And that during these shock predictive cues, the directionality of BLA to PL seems to dominate. So perhaps that is suggesting a bottom-up, process that's occurring in the face of these shock predictive cues. And that's, of course, speculation. Right? We also showed you that decoding accuracy is greater in these BLA to PL neurons, and that's significantly higher when we know the identity of the neurons versus when we don't. And so just to put this back together with what else we know, we can think of the basolateral amygdala as having diverse projections to striatal-like structures as well as cortical structures, and that the outputs to striatal-like structures might be more important for action selection and behavioral output, but BLA input to cortical regions might be more important for this orchestration of competing motivational drives. And so we have a lot of future directions that we're interested in, but I'll end there for interest in time. And I want to again thank the people in my lab who did the work. I talked about work from Gwendolyn Calhoun and Amy Sutton, following up on work from Anna Taylor, who's now starting her own faculty position at the University of Bordeaux, very talented scientist, Anna, and Praneet. And then Tony and Eyal got it blocked out this part, but Tony led the more recent sort of mechanism orchestration project. And I'll thank my collaborators, many collaborators that I didn't have to talk about today, our funding sources, and all of you for your attention.
So before we start with the questions, we have a block actually. This is a distinguished lecture, and distinguished lectures come with blocks. And this is a very complete block which we'll mail to you, so you won't have to take it home with you. So again, thank you for coming. This is really wonderful. We have time for a number of questions. Actually, I will start. You showed with Carl that you can manipulate the dopaminergic neurons and affect depression behaviors. And we know that depression changes, reward and threat, right? So I'm wondering, you must have looked at this to see whether optogenetically manipulating these neurons changes how this circuit, regulates, reward and threat.
You mean manipulating PTA neurons?
Exactly, yeah. Maybe brain dopaminergic neurons.
So that is something that we're working on now, how dopamine modulates neurons that encode reward and aversion, but it's actually not trivial to be able to report from the identified neurons and stimulate at the same time. So I guess a lot of the delay for why we haven't gotten further with that is sort of technical reasons, not particularly interesting, but essentially to stimulate an input like dopamine terminals into a region and also photo-identify different populations of neurons essentially requires two opsins, and every redshifted opsin has like this blue shoulder. So actually that's a major, to me that's almost a very, very challenging sort of potential confound or artifact that is almost prohibitive, but now we're moving forward with imaging, and with GCAM you need such lower levels of likely photo identification. So we are pursuing that project now, but still very much a work in progress.
I'm interested in the last thing that you showed, I'm interested in the last portion that you showed where you were co-presenting both the positive and quote-unquote negative stimulus. And I'm interested because you have sucrose, the positive reward, coming before the foot shock. And I'm wondering if you think that has an effect on, first of all, the actual choosing. So it seemed like you had a overpreponderance when you looked individually at choosing the sucrose over using. And also if you think that then the directionality of the neurons might be shifted in any way.
That's a great question. So, in our particular case, we're doing sucrose delivery to the port. So, and you're right, absolutely, shock is at the end of the queue. So another thing I didn't tell you about, which could contribute. So first, I think the first question you asked is this bias towards port entry, typical? But I'll say there's very diverse responses. There are some rats that freeze to every cue during the compensatory trials, regardless. And some rats always go to the port, and then some rats that sort of waffle in between, depending on the trial, select one output or the other. And right now it's basically, ends up being 50-50. We also could do a slightly different paradigm. And some people in the lab have taken to that where we titrate the sucrose in shock levels so that every animal is sort of roughly 50-50. That is another way to do things, but we were sort of using that behavioral variability as sort of a tool instead of trying to get all the animals to 50-50. So that's something else we could do. When we start pumping the sucrose, it doesn't necessarily mean that the animals will collect it, but you're right. And the other caveat is that we train the animals to perform just the sucrose, the Pavlovian conditioned approach, before we introduce the shock cue, because if we introduce them at the same time, the animals just don't do anything, they just freeze. So it's sort of, there is some inherent asymmetry in reward learning and fear-related learning. So, I don't really see a way to get around that, but if you have suggestions, I'd love to hear them. But to answer your question, that wasn't necessarily representative. I mean, there's some animals that, it's like probably, I would say 3 categories of animals. Ones that always do fear behavior, ones that always do reward behavior, and some that sort of depend. So that's not necessarily the case. Overall, it's pretty much in the smack dab in the middle of the average overall population. But all those smaller parameters to play with, I think that's something we're very interested in doing. This is sort of just the first, the first prototype of this behavioral paradigm, so we're still working through that. But thanks.
I just had a few questions about the decoding itself. Over what duration or what interval in the childhood are you decoding? Because presumably those seemingly non-coding neurons might be part of the decision process. So if you look at the beginning of the first second or so, you're not see the decision emerge. I'm just curious.
Yes, no, so we've done it a few different ways. We've done it using the entire queue. Obviously that has the potential confound that they're actually getting the US. We've also done, we haven't done the first second or two. A lot of these neurons are very low firing, and so they're so sparsely populated that we sort of struggled to which we tried it with. I wanted to initially try the first 500 milliseconds, but there was just too few spikes. But if we use the first 5 seconds before anything is delivered, we already see an emergence you can see a significant prediction of BLA to PL neurons that is already more accurate than other neurons. So I agree. It's possible that it's a decision-making process. Another completely, possible interpretation is actually it's not decision-making necessarily, it's perception. It can be related to the actual perception of the cue. And so one way to tease that apart is to try to manipulate these neurons, starting our manipulation at different points in the cue. Right, so the perception might be, I would imagine, at the very beginning, but I think teasing apart whether what we're looking at, it has to do with what the animal just has, what features of the stimuli the animal happens to be attending to, or if it's actually decision making. I mean, I might argue that determining what to pay attention to and decision making are not independent processes, but that's an excellent question, and we're thinking about that very much right now. So yeah, that is what we are imagining that it is the emergence of such.
In the first part of the talk, you showed that the C to N excitation was state.
Sorry?
The C to N excitation was state dependent.
Yes.
The neurons that the mechanism for that?
Very good question. So we are exploring that. Our 2 main ideas. It's a little bit of a fishing expedition, so I promised my postdoc that I would take 2 hypothesis test. If it doesn't work out, then so the first thing that I think the 2 likely hypotheses are that some specific input, Bo Lee and Rick Perker have shown, and actually Mark Anneman have suggested that PBT to BLA could be a potential input that plays a role. Another possibility is we know that BLA neurons express ghrelin receptors. We don't know if ghrelin receptors are selectively expressed on one population or another. That's something that we're exploring. So ghrelin or other hormonal signals for energy balance. So maybe there's something direct, just of sensing energy balance, or it could be some sort of thalamic or hypothalamic input to BLA. So that's a lot of possibilities, but those are our ideas for what the mechanism might be. And we're also just determining if increased excitability of BLA accumbens neurons is essentially the effective mechanism. If we block that, are we, blocking the behavioral effects of food restriction? That surprisingly. But that's, you know, something that we're testing right now as well.
Chris.
So in this competition, are they food restricted? Yeah.
Yes, they are.
So have you tried not food restricted women, restricted Hughes?
So we've done some pilots with that. If we don't food restrict them, essentially what happens is the animals don't go to the port, and then they just, even though, I mean, it's really weird because going to the port doesn't increase the likelihood that they're going to be shocked, that they're just going to be shocked no matter what. So it's not really, to me, you know, it's not really clear to me why that is the case, but port entries drop when the animals are sated and they just sort of don't attend to those cues. So it's a little bit tricky from that perspective. Not food restricting them just makes them not do the reward, the appetitive behaviors. So that's the challenge. But ideally, that's what we're doing with the head fixed imaging task. So we're head fixing the animals, and then we're going to image in sated conditions and as well as vet as restricted conditions, and look at the same neurons and how they respond when we do just play the cues passively. So for this particular task, it doesn't, you know, there's some confounds because now the animals aren't going. So is the representation changing? Because there's, you know, so, but that's exactly what we're doing right now with the 2P experiments. I showed you like a fanciful, you know, hopeful slide in the future.
And just to follow up what Chris said, so when they're not going to the port, are they freezing, right? Because they, you know, there's a third state where
Right,
they're not going to
just
the port,
hanging
they're
out.
not freezing,
That's
they're
right.
just moving around.
That's right. So, yeah, I think when they're not going to the port and not freezing, you know, we show that it's just black. It's just black. It's just neither.
So if they're not
there's-
food restricted, maybe they'll be more black. That's what you would expect.
Oh, I see what you're saying. Actually, yes, that's what we see. We see a little bit more black, just a lot less blue. They still freeze a good amount, but actually it seems like slightly less. I mean, it's just a couple of pilot animals, so we don't know the end. I can't give you a firm answer just yet.
It was another. Yes.
So in the competition mode, is it, I'm trying to phrase this correctly, is it equally likely that if you present that if they start heading toward the port that they won't freeze versus if they start freezing that they won't head to the port? In other words...
Right. It seems to be what's happening. I mean, what we observe is that, you know, the animals sort of select whatever behavior and then typically hold that across. We have one animal that's a waffler, but it's sort of the anomaly. So, yeah, I'm not sure I understand.
Yeah.
Okay, one last question. Back there, it's been waiting.
So the cartoon was really clever because the mouse can't escape in the cartoon, but normally if you saw a cat, he could run and escape. So
Right.
have you considered making the shock condition escapable so the animals really have to choose?
Exactly. So that's exactly the other variation. So we've already run all these animals on, well, it's slightly different. It's not, it's a slightly different task, but where the shock is a choice, right? There's a safe platform. The animal does not have to step on the shock cube, on the shock grid if they don't want to. And in this particular case, they have to cross a shock grid to collect the sugar. So it's slightly different, but where there's a choice. And we've done all the recordings. We just, you know, you should help me email Tony and tell him to analyze the data. Yeah, we have those data. We haven't slugged through all the analysis yet. The behavioral scoring of that task, for whatever reason, is just a little trickier. So, for uninteresting reasons. But yes, exactly. We've collected those data. We just haven't analyzed it yet.
So once again, please join me.
Thank you.